whatever. Just take a second and look up.
At the ceiling or maybe the sky if you're outside.
Yeah. It looks pretty empty, doesn't it?
Just open space.
Exactly. It looks like nothing. But what if I told you that you are currently, right this second, walking around at the bottom of a massive ocean?
Not an ocean of water, of course.
No, an ocean of air.
Wow.
We are living our lives under a layer of atmosphere that is roughly, 50 kilometers thick?
It's a staggering thought when you actually stop to analyze it. We feel light, but we're constantly supporting this immense weight on our shoulders.
We just don't notice it.
Nope. It's our natural habitat. We evolved in it.
And that weight, that invisible ocean, it creates pressure. Today, we're taking a deep dive into a document that usually only sees the inside of a workshop or a classroom for instrument technicians.
It's from the Northern and Southern Alberta Institutes of Technology. And the title is very simple: Pressure Measurement.
I know what you're thinking. Pressure measurement. It sounds like maybe the driest topic we could possibly pick.
Oh, I thought so too at first. But I promise you, having gone through this, the physics hidden in these pages explains how the entire world works.
It really does. This isn't just about, reading a dial on a dashboard. It's about decoding the invisible forces that keep airplanes flying or keep pipelines from bursting.
Or even just why your ears pop when you drive up a mountain.
Exactly. So our mission today is to take these technical concepts, which can get pretty dense, and just decode them. We're going to look at the physics of liquids, the definition of pressure, and the obsessive, almost paranoid level of precision you need to measure it right.
And precision is the key word. In the industrial world, if you misunderstand the relationship between mass, force, and area, things don't just stop working.
They break.
They break. And sometimes they explode.
So, no pressure, pun intended. Let's start at the very bottom, the building blocks. The manual kicks off with a formula that seems simple, but it's doing a lot of work. Pressure equals force divided by area. P equals F over A.
Right. That's the fundamental equation. And to visualize it, the text uses this 1-inch block analogy, which I love.
Yeah.
It just strips away all the complex machinery.
So imagine a simple wooden block.
Yep. 1 inch wide, 1 inch long, and it weighs exactly 1 pound.
Okay, I'm picturing it. A little cube of wood.
You set that block on a table. The area touching the table is exactly 1 square inch.
Right.
The force pushing down, thanks to gravity, is 1 pound. So you get 1 pound per square inch, 1 CSI.
Simple enough, but here's where my brain starts working. If I take a second identical block and I balance it on top of the first one.
What happens to the area touching the table?
Well, it hasn't changed. It's still just that 1 square inch at the bottom, but now I've got 2 pounds pushing down.
So the force doubled, the area stayed the same.
Which means the pressure is now 2 psi.
Exactly. You've increased the concentration of the force. That's what pressure is. But, and this is where the manual gets very specific, we have to talk about the difference between weight and mass.
Oh boy. Okay, let's unpack this. This feels like a flashback to high school physics because it's a distinction we totally ignore in daily life, right? I buy a pound of coffee. I don't care if it's mass or weight. It's just heavy.
And for buying coffee, no, it doesn't matter. But for engineering a high-pressure gas line, it matters a whole lot. Mass is the amount of stuff in an object.
The actual matter.
The matter, yeah. And it's independent of gravity. If you take that 1 pound block to the moon, it still has the same amount of wood in it. Its mass is identical.
But if I put it on a scale on the moon?
It would barely register anything. Because weight is a force. It's what happens when gravity grabs that mass and pulls on it. The moon's gravity is weaker, so the weight is less.
So why does this matter to a technician on Earth? They're not recalibrating gauges on the moon.
No, but there are calculating forces based on physical laws. In the metric system, the SI system, we get really sloppy. We say something weighs 10 kilograms. That's actually wrong.
Mass is kilograms.
Mass is kilograms. Force is newtons. The manual points to Newton's second law. Force equals mass times acceleration. F equals ma.
And in this case, acceleration is gravity.
That's gravity, exactly. F equals mg. So if you're calculating pressure, you're really calculating the mass of a fluid times the acceleration of gravity all spread over an area. Confuse mass and weight, and all your mass just falls apart.
Okay, so we have mass, force, area, but there's another variable that feels like it should be constant, but the manual says not so fast. Density.
Ah, yes, rho. That's the Greek letter. And relative density.
And relative density is just comparing something to water, right? Like, is this oil heavier or lighter than water?
Essentially, yes. It's a ratio. If something has a relative density of 0.8, it's 80% as dense as water, so it floats. But there's a catch. The manual makes a very specific point. Water isn't always the same density.
Wait, what? I thought water was the baseline. Like, 1,000 kilograms per cubic meter, period.
It is, but only at 4 degrees Celsius.
That is so specific. Why 4 degrees?
That's water's point of maximum density. It's when it's most compact. As it gets colder and turns to ice, it expands. That's why ice floats, right?
Right.
But as it warms up above 4 degrees, it also expands. The molecules get more excited and they push each other apart.
So if I'm doing a calculation for a refinery and I just assume water is a neat 1,000 kilogm3, but the water in my pipe is actually at room temperature, say 20 Celsius?
You're going to be wrong. At 20 degrees, the density drops to about 998.280 kilograms per cubic meter.
998 versus 1,000. I mean, that sounds like such a tiny difference.
In baking a cake, sure. But in precision instrumentation, where you're measuring millions of barrels of oil, those little decimals add up really fast. That tiny error means you think one thing is happening, but something else is actually happening.
Wow. It's like the truth of the measurement depends on the room's thermostat.
Welcome to metrology, the science of measurement. Nothing is as simple as it looks.
Okay, so we've got force, area, and density that changes with temperature. Now, here's where it gets really interesting. Hydrostatics. Fluids at rest. And this is where my intuition just started to completely fail me.
You're not alone. Hydrostatics is famous for being a brain bender.
Okay, let's talk about the direction of pressure. The source describes this experiment with mercury tubes.
Right. Imagine you have 3 glass tubes with mercury in them. You lower them all into a big tank of water. One tube's opening faces up, one faces down, and one faces sideways.
And they're all at the exact same depth. My gut tells me the one facing up should feel more pressure. The water is pushing down on it.
That's the intuitive thought. Pressure pushes down.
But that's not what happens, is it?
Nope. The mercury gets pushed back up the tube the exact same distance in all 3 tubes.
So the water is squeezing from the side just as hard as it's pushing from the top.
Exactly. At a specific depth, fluid pressure is uniform in every single direction. It's not a weight on your head, it's a crushing force from all angles.
Which explains why submarines get crushed like a soda can if they go too deep. It's not the roof caving in, it's everything at once.
It's omnidirectional, which leads right into the second mind bender. Pascal's vases.
I loved the diagram for this. It looks like a mad scientist slab. You have these different shaped glass containers all connected at the bottom. One is a super skinny tube, one's a giant cone, one's a giant cone, one's a weird wiggly shape.
Then when you pour water in, the level settles at the exact same height in all of them.
But hold on, the giant cone holds like 10 times more water than the skinny tube. That's 10 times the weight. Shouldn't that extra weight push the water higher in the other tubes?
You would think so, but no.
Yeah.
The shape of the container doesn't matter. The total volume of water doesn't matter.
That just feels wrong. If I have a swimming pool connected to a drinking straw, the pressure at the bottom of the pool has to be higher.
It feels wrong because we're confusing total weight with pressure. Remember, P equals F over A. The pool has way more weight, yes, but it also has a much, much larger area at the bottom to spread that weight out over. The pressure at the bottom is only determined by 2 things.
Let me guess. Height and density.
Height of the fluid and the density of the fluid. That is it. The formula is P equals rho GH. Density times gravity times height. There's no width of the tank in there.
So if I dive 10 feet deep in a backyard pool, or I dive 10 feet deep in a massive hydroelectric reservoir,
The pressure on your eardrums is identical. The millions of gallons to your left and right in the reservoir mean nothing to the pressure right where you are. Only the column of water directly above you counts.
okay, my brain is protesting, but I accept the math. Let's talk about the fluid itself. The manual mentions mercury a lot. Why are we so obsessed with this toxic metal?
It all comes back to density. Mercury is about 13.6 times denser than water.
So it's incredibly heavy.
Incredibly heavy. Which means a column of mercury only needs to be a fraction of the height to exert the same pressure as a column of water.
Ah, I see where this is going. If I wanted to measure atmospheric pressure with a column of water.
You'd need a glass tube about 10 meters tall, over 30 feet. Not exactly practical.
But with mercury.
You only need about 760 millimeters or roughly 30 inches. That's a manageable size. That's why old barometers used it.
Speaking of instruments, let's get into the gear. The tools of the trade. The manual draws this hard line between primary standards and secondary standards. What's the difference?
It all comes down to trust. A secondary standard is what you see in the field, like a gauge on a pump. It's useful, but how do you know it's accurate?
You check it against something you trust more.
Right. But eventually that chain has to end somewhere. It ends at a primary standard. Primary standard doesn't need to be calibrated because it is based on fundamental physical laws. It defines the measurement.
And the king of these seems to be the deadweight tester, or DWT.
It's a brilliant piece of engineering. And deadweight is literal. It uses actual dead weights.
Walk me through it. How does it work?
Okay, imagine a vertical cylinder filled with oil. Inside is a piston that fits perfectly. Machined to microscopic tolerances. You then place these very precise certified metal weights on top of that piston.
So you're using gravity to push the piston down into the oil?
Exactly, force over area. You know the exact mass of the weights. You know the exact area of the piston, so the pressure you are generating in that oil is a mathematical fact. It is truth.
So you hook up your regular field gauge, see if it matches the truth, and adjust it if it's off.
That's the idea. But there's a trick to operating it. The piston doesn't just sit there. It has to float.
Float?
You pump oil in until the weights actually lift off their base. They just hover, supported only by the oil. And then, and this is the part that always looks weird, you have to spin the weights.
Spin them like a top.
Yeah, you give them a gentle spin with your hand.
Why? What on earth does that do?
It's all about friction. Even with a perfect fit, the piston is touching the cylinder walls. That static friction would throw off your measurement.
Ah, so spinning it breaks that friction.
It breaks it, and it centers the piston perfectly in the fluid. It ensures the only force is from the weights.
That is just so elegant. And for really low pressures, they use a pneumatic version with air.
Yes, and those don't even use a piston. The manual mentioned a ceramic ball.
Right.
It's a precision ceramic sphere floating in a nozzle of air. It acts like a perfect, self-centering spherical piston. Incredibly accurate for tiny pressures.
Okay, so that's the heavy machinery. But there are also manometers. The classic U-tube seems way simpler.
The U-tube is the grandfather of pressure measurement. It's just a glass tube shaped like a U. You put liquid in it. If the pressure is equal on both sides, the levels are even.
Push on one side, the liquid goes down on that side and up on the other.
And you just measure the difference in height with a ruler. Simple.
But the manual also detailed the Wella manometer, which sounded more convenient because you only have to read one level.
Right. In a U-tube, you have to do math. Left side is down 2 inches, right side is up 2, so the total is 4. It's easy to make a mistake. A well manometer makes one side enormous a well.
So when the liquid rises in the skinny tube, the level in the wide well barely drops.
Barely. So you only have to read the one rising scale. But there was a really specific warning in the text about that scale. Did you see that?
I did. It said you can never, ever swap the ruler from one well manometer to another.
Exactly, because the level in the well does drop, even if it's a tiny bit. So the manufacturer actually shrinks the markings on the ruler to compensate for that drop. The inches on that scale aren't true inches.
So if you broke one and grabbed the ruler from another gauge...
all your readings would be wrong and you'd have no idea why.
Wow. Okay, one more type. The inclined manometer. This one was clever.
This is for measuring really, really tiny pressures, like the draft in a furnace or airflow in a duct.
So how does it work?
You take that vertical glass tube and you lay it almost flat on a long, gentle slope. To get the liquid to rise vertically by just 1 inch, it might have to travel sideways along the glass for 10 inches.
Oh, I get it. It magnifies the movement.
It stretches out the reading, exactly. A tiny flicker in pressure becomes this big, easy-to-read movement along the inclined tube. It's just geometric amplification.
Okay, so we've got spinning weights and tilting tubes. Now we need to talk about the numbers themselves, the scales, because 0 isn't always 0.
This is one of the most important concepts. We have 2 main reference points. One is a perfect vacuum, true 0, no molecules. The other is the pressure of the room you're in right now.
Which brings us back to that 50-kilometer blanket of air. At sea level, that's pushing down with about 14.7 psi.
Right. So, when you check your car's tire pressure and the gauge says 32 psi, what is it really saying?
It has 32 pounds of pressure in it.
It's saying your tire has 32 psi more pressure than the outside air. If that gauge read 0, it wouldn't mean the tire's empty. It would just mean the pressure inside is the same as outside.
Ah, so that's gauge pressure. It uses the atmosphere as its 0 point.
Exactly, or sig. But sometimes, for science, you need to know the total pressure. From a perfect vacuum up, that's absolute pressure.
So what does this all mean? Absolute pressure is what the gauge says, plus the atmospheric pressure.
Correct. So your 32 psi tire actually has an absolute pressure of 32 plus 14.7. So about 46.7 psi.
And a vacuum measurement, that's suction.
Well, suction isn't really a thing. Vacuum is just measuring how far below atmospheric pressure you are.
The manual had a great visual. 3 gauges on one tank: absolute, gauge, and vacuum.
Okay, let's walk through it. Say the pressure in the tank is exactly the same as the room.
The gauge pressure reads 0. The vacuum gauge reads 0.
But the absolute gauge reads 14.7 psi because it sees that blanket of air.
It never ignores the atmosphere.
Never. Now, you suck some air out of the tank. The gauge pressure can't read negative, so it stays at 0. The vacuum gauge starts to climb, telling you how much suction you have.
And the absolute gauge starts dropping down toward true 0.
Exactly. It's like having 3 watches set to 3 different time zones. If you confuse absolute and gauge pressure in a calculation, you could be off by almost 15 psi right from the start.
And that could be catastrophic.
And it gets worse because atmospheric pressure changes. It changes with the weather and with altitude. Calgary has a lower atmospheric pressure than Vancouver.
So a gauge calibrated in Vancouver might read wrong in Calgary.
It absolutely could. Its 0 reference point has physically shifted.
This brings us to the so what of this whole deep dive. The level of precision in this manual is it's mind-blowing. It feels like they're chasing a perfection that doesn't even exist.
It really is about precision. And there was one final detail that stuck with me. It was about gravity, the letter G.
Yeah.
We learned in school that it's a constant, right? 9.81 meters per second squared.
A useful lie, isn't it?
It is. The Earth isn't a perfect sphere. It bulges at the equator. The rock density changes.
Yeah.
So gravity in one city might be 9.81, and in another it's 9.78.
And since pressure depends on force, and force depends on gravity.
If your local gravity is different, your deadweight tester, that perfect primary standard, is actually generating a slightly different pressure. The manual says high-end calibration requires you to correct for where you are standing on the planet.
That is it's incredible. We assume a pound is a pound. But here, the latitude of your workshop changes the truth of your measurement.
It shows a measurement isn't just finding a number, it's an estimation of the truth. And we're always trying to get closer, but there are always these variables, temperature, gravity, air density, pulling us away.
It leaves me with this thought. If these professionals have to account for the curvature of the Earth just to measure pressure correctly, how much error do we just accept in our daily lives without even realizing it? How many facts that we operate on are really just close enough?
That's a very healthy skepticism to have. The world is a lot more fluid, pun intended, than we think.
On that note, I'm going to go appreciate the 50 kilometers of air on my shoulders a little more. Thanks for listening to this deep dive.
Always a pleasure.
We'll see you on the next one.